Hello everyone. So in today's video, I want to show you something that is both interesting and useful. And this is a technique for computing Laplace transforms of functions without using integration at all, without using first principles. And so we're going to apply this technique to a few examples just to show you how it works. But the technique really applies to many more functions than are listed here. And so the real value of the video here is just to try and absorb the technique so that you can apply it in whatever examples you choose. And then at the end of the video, I want to show you something also quite interesting, which is got to do with this trigonometric identity here. And the question you may ask is, what does this have to do with Laplace transforms? All right, so let's jump straight in and just recap some very small basics of Laplace transforms. And that is these three properties. So all of these properties have been dealt with in previous videos. So if you really want to see where these formulas come from, just check out those videos. But we're just going to be using these three properties alone. So the first property here is called linearity, which is a good name because it just says that the Laplace transform of a linear combination is the linear combination of the corresponding Laplace transforms. The second formula here is just a well-known formula for Laplace transforms. It's actually very easy to derive, and you can see that in one of my videos. But it gives us a formula for computing the Laplace transform of the derivative of a function, and that formula is just given here. So the Laplace transform of y prime is s times the Laplace transform of y minus y at 0. And then you can apply this formula over and over again to get Laplace transforms of higher derivatives. And so we can get a formula like this, for example. Okay, so let's get straight to it and see an example. So here we are looking at this Laplace transform of the function y equal to 1. Okay, so not the most difficult Laplace transform, but we're just interested in this for the technique reasons. So if y is equal to 1, where does the technique begin? Well, it begins by differentiating both sides here to get y prime is equal to 0. We're looking for a differential equation which y is the solution to, the unique solution to. Now at this point, when you've got such a differential equation, you can apply the formula for the derivative of the Laplace transform of the derivative of the function. And so here, just applying Laplace transform to both sides, we get L of y prime is just equal to L of 0. And that tells us that S times the Laplace transform of y minus y at 0 is just equal to 0. Because the Laplace transform of 0 is just 0. And then we just applied the formula given here to the left-hand side of this equation. Great. And now if we look at, what are the unknowns here? Well, this we need to replace by an actual number. And y of 0 is just clearly equal to 1 because the function here is just the constant function 1. And so what do we get? What is the end result? We get s times L of y minus 1 equals 0. And so s times L of y is just equal to 1. And so we have our Laplace transform. It's just divide both sides by s and get 1 over s. And you can see here, as promised, no integration was done at all. But this is a very easy example, so maybe we need to look at something slightly more difficult. So let's look at this function here, y is equal to t. Okay, so if y is equal to t, then let's differentiate both sides again to get y prime is just equal to 1. And here we're in a position to apply the Laplace transform to both sides. And why is that? Because we know what the Laplace transform of this is. We just calculated that. And so let's do that. Here we'll just get the Laplace transform of y prime is just equal to the Laplace transform of 1. And this tells us that s times the Laplace transform of y minus y of 0 is equal to the Laplace transform of 1, which we just saw was 1 over s. Okay, so now let's see, what is y of 0? Well, y of 0 here is plug in t equal to 0 and you just get 0. So here you just get s times the Laplace transform of y minus 0 is equal to 1 over s. And again, dividing both sides by s, you get 1 over s squared is the Laplace transform of y in this case. Okay, great. So 2 examples down. Let's see if we can get another one under the belt. Here is the Laplace transform of e to the t. Okay, so what do we do here? Well, again, we have y prime is just equal to e to the power of t. The derivative of y is just e to the power of t. Okay, and we can continue differentiating, but nothing much is going to change. But here's another trick. If y prime is equal to y, then this is what we have. And so we can construct a differential equation. Y prime minus y is equal to 0. And now we're in a position to apply a Laplace transform to both sides and use the formula 2 here. So let's do that. We take the Laplace transform of both sides. Y prime minus y is equal to the Laplace transform of 0, which is 0. And now we can use the first rule here, linearity, and we can apply it to this expression here and get L of y prime minus L of y is just equal to 0. Good. And let's now use the formula 2 here. So just this formula on this expression to get that s times the Laplace transform of y minus y of 0 minus L of y is all equal to 0. And what is our job at this point? Our job is to simply solve for L of y, in this equation here. Why? Because it's just an algebraic equation in L and S. This here is a number, and in particular, y of 0 is just equal to e to the 0, which is 1. And so this just ends up being s times L of y minus 1 minus L of y is equal to 0. And let's take the 1 over and factor out let's actually just do 2 steps here. So we get this, and then finally we get s times the Laplace transform of y times s minus 1 is equal to 1. And then from this equation, we're in a position to divide both sides by s minus 1, and then we get exactly what we need. The Laplace transform of e to the t, or y, is just 1 over s minus 1. And you can see, as promised, no integration at all, which is very nice. So let's look at another example to try and see the technique in action here. So here we're asked to calculate the Laplace transform of this trigonometric function, sine 2t. Okay, so this will be a little bit more. We have to do a bit more here. But if we have y is equal to sine 2t, then the derivative here is just equal to 2 cos 2t, and the second derivative here is just equal to negative 4 sine 2t. Right, why did we differentiate twice here? Because let's say I stopped here. Then if I applied the Laplace transform to both sides, I would still be left with the problem of calculating this Laplace transform, the Laplace transform of cos 2t. And we don't know what that is at this point. So when we have such a term where we don't know what the Laplace transform is, we continue going and we apply Laplace transform even once more. So that's when we get here. Now, why do we stop here? The reason is because the sine 2t can be replaced by a y. And what is the resulting equation here? Well, the resulting equation is just that y double prime minus 4 sine 2t equals 0. So in other words, y double prime, plus here, y double prime plus 4y is equal to 0. Great, and now we're in a situation where we can use our formulas. So let's apply the Laplace transform to both sides. So we have to use linearity here. So the Laplace transform of the left is just this, the Laplace transform of the right is just going to be 0. And then what are we left with? Well, this will just be Laplace transform of the second derivative plus 4 times the Laplace transform of y is all equal to 0. Great, so now we're in a position to use this formula here. And let's do exactly that. So we get that this is just equal to s squared times the Laplace transform of y. And then we have to subtract s times y of 0 minus y prime of 0. And this should be, and then I have to remember to add 4 times the Laplace transform of y. All of this should be equal to 0. Okay, so just to be clear, this here is just exactly equal to this. And then I did nothing to the 4ly. So we really are dealing with the same equation here. Good. So now what do I need to do? Well, I need to know what these are. But I've calculated these derivatives. So y of 0 is just equal to what? Well, sine of 2 times 0 is sine of 0, and that's just 0. Okay, y prime of 0, what is that? Well, if I plug in 0 into this equation here, what will I get? I will just get 2, because 2 times cos of 0 is just 2. Great, so let's plug that in and get s squared times L of y minus 2 times y of 0. So we just get 0 here. I'm just going to actually just put the 0 here because s times 0 is 0. And then minus y prime of 0, which we just said was 2. So and I then add 4 times L of y. And this is just equal to 0. Okay, great. And now here we just can simplify the equation. So what I'll do is just take this negative 2 over and get that s squared L of y plus 4 L of y is just equal to 2. And again, this we can factor out the L of y. What are we doing here? We're just solving for the L of y. So we get L of y times s squared plus 4 is just equal to 2. And so we've just calculated a Laplace transform. How? We just divide both sides by s squared plus 4. And so here we just get 2 over s squared plus 4. It's as easy as that. 2 over s squared plus 4. All right, so we're starting to get a feel for the technique here. So let's look at a non-standard example of a Laplace transform. Let's look at this example here. So y is now equal to sine squared of t, and we're looking for the Laplace transform. So again, we have y is equal to sine squared of t, and so we can differentiate here. And what do we get? Well, we get 2 sine t times cos t, right? Because this here is just equal to sine squared t, sine of t squared. And we can just apply the chain rule. Great, and here, what is this equal to? It's actually magical that this here turns out to just be sine 2t. So very, very nice formula here. All right, and now we're in a position to apply the Laplace transform. So we've just seen that y prime is equal to sine 2t. And so we can apply the Laplace transform to both sides. L of y prime is just equal to L of sine of 2t. And here we know what this is because we calculated it in the previous example, and we can just apply our formula here to, at number 2. So this will just end up being s times L of y minus y of 0 is equal to what we calculated in the previous step, which, if you remember, was just 2 over s squared plus 4. So here, let's see what we get. This is s times the Laplace transform of y minus y of 0. But what is y of 0? Well, you can see this here will just tell us y of 0 is equal to 0. 0 squared is 0. So here I just get this. And finally, I just get the Laplace transform of y. In fact, I'll write it in the box. Is just divide both sides by s. And so we get 2 over s times s squared plus 4. Very nice. Okay, great. So that gives us a good example, a good illustration of how to apply this technique. You can apply this technique in many different situations. And now let's look at a quite difficult example of how the technique can be used. And here is that example. Sine cubed. So this is going to be a bit more challenging. But I want you to just think about how difficult this would be to calculate from first principles. This would be an integral involving the product of e to the negative st and this function, and that would be very, very difficult to calculate. So let's see how we can use our technique here. So the first thing what I want to do is, if I have y is equal to sine cubed of t, I want to involve the fundamental trigonometric identity, sine squared plus cos squared equals 1. So what I'm doing is here, I'm writing this as sine of t times sine squared of t, so that this ends up just being sine of t times 1 minus cos squared of t, and this is just sine of t minus sine squared t times, sorry, not sine squared, what am I saying? Sine of t times cos squared of t. Okay, so this is something we're going to keep in the back of our minds, because it's going to give us this important formula here, which is that I'm going to, so I have y is equal to this. So what I'm going to do is shift the sine t over, and then multiply by -1. So in other words, the exact same equation just rearranged is going to tell you that, let's see here, sine of t minus y is equal to sine of t times cos squared of t. Okay. So this is an important thing that we're going to be using momentarily. All right, great. So we'll just store that away for the moment. But now let's get back to our technique. So firstly, our technique says we have an unknown Laplace transform. We want to calculate the Laplace transform of sine cubed of t. So what are we going to do? We're going to differentiate a few times. So we're going to take the first derivative here and get 3 sine squared t times cos of t. Okay? And we can see here we're not in a position to simplify anything. So what do? We differentiate again. And we get y double prime is equal to, so I differentiate, this is a product of functions, so I differentiate left-hand side here, this first product, so I get 6 sine t times cos t, and then the cos t will multiply with this one to get cos squared of t. All right, so that's what I get when I differentiate this function and multiply it with this one. And now what we're going to do is differentiate this function and multiply it with this one. So what do I get? I get minus sine of t times this function. So I'll just put that here, minus sine squared of t, sorry, 3 sine squared t, and so this is just equal to 6 sine t cos squared of t minus 3 sine cubed of t. Okay. Now we are doing something very useful. We're cooking with gas here, because this thing, sine t times cos squared t, appears here. And sine cubed t is exactly what y is equal to. So our equation is going to simplify a lot. What are we going to get? So y double prime is going to be equal to, so 6 times sine t times cos squared t, which is just sine of t minus y. How did that happen? That just happened because of this identity here. This is equal to this. Okay, easy as that. And now I say minus, so minus 3 times sine cubed, but as we saw earlier, sine cubed is just t, so this is just minus 3y. Okay, great. So let's take the 3y over, and we get y double prime plus 3y is equal to 6 sine t minus 6y is equal to, so these things are equal. And so finally here, we get y, so I'm just going to take the 6y over now, and I get y double prime plus 9y, because the 6y will combine with the 3y to give us 9y, is equal to 6 sine of t. Okay. Great. And this is very good news. Why is this very good news? Because we can apply our formula here to this side, and we know what the Laplace transform of sine of t is. I know, what do we know? What is that Laplace transform? Let's just write it down. The Laplace transform of sine of t. By the way, you could compute this so easily using our exact technique, which we've been doing the whole video. But this is just equal to 1 over s squared plus 1. Okay? So using that fact, let's apply the Laplace transform here to both sides of this equation. And so we get the Laplace transform of y double prime plus 9y is equal to 6 times 1 over s squared plus 1. And so here we get that if I take the Laplace transform of y double prime, so what I'm going to do is just apply the linearity here to this expression. So I write down first the Laplace transform of y double prime. But let's immediately use our formula so that we don't waste any more time here. So using our formula, we get s squared times the Laplace transform of y minus s times y of 0. But what is y of 0? Y of 0 is just 0 because sine cubed of 0 is 0. Great. So this term falls. So this term here is 0. And now I take y prime of 0. And now what is y prime of 0? Well, here's the derivative. And what happens when I plug in 0? Well, the sine squared of t will make everything 0. Sine squared of 0 will make everything 0. So what we get is that y prime of 0 is also equal to 0. Great. And so what the Laplace transform of y double prime is it just turns out to be equal to this. Great. So now we've got that, and now we have to add 9 times the Laplace transform of y. Okay, and this is equal to 6 over s squared plus 1. And so let's just make one last equation here. We get the Laplace transform of y times s squared plus 9 is equal to 1 over s squared plus 1, I think. Okay. And so what do we do again? We divide both sides by this term here, and we get the Laplace transform here. It is just exactly equal to 1 divided by s squared plus 1 times by, not 1, sorry, it's not 1 here. There's a 6 here, I forgot. So 6 over s squared plus 1, and then here I have s squared plus 9. Okay, and that's our Laplace transform. So this is a very interesting example of how we can use the technique. And again, we used no integration whatsoever. So very interesting. All right, let's now take a look at an interesting little observation here. So we just computed the Laplace transform of y of sine cubed, right? And then there's this weird formula given here, trigonometric identity. I just want to show you how this formula can be obtained using Laplace transforms. So, first things first, we said that the Laplace transform of this sine cubed of t, we just calculated that, this is equal to, as we said, 6 divided by s squared plus 1 and then s squared plus 9, right? Now, this fraction here can decompose. Every fraction of this form can decompose into partial fractions, right? So we can write this as, in a certain way, we can write this as something divided by s squared plus 1, and then plus something divided by s squared plus 9. That's the partial fraction decomposition. You can always do this. Now, what will that something be? In this case, you can check, but it'll be 3 over 4. I'll leave you to calculate that if you're interested. And here, this will be negative 3 over 4. Okay. And then everything works out. If you add these two fractions, you'll get this one. Now, why do I do this? Because if we apply Laplace transform, the inverse Laplace transform to both sides, so we take the inverse Laplace transform of this, which is this, what are we going to get? By the way, I'm just going to write this a bit differently. So this is 3, in fact, let me just copy it. It's probably the easiest. It's not copying, 1 second. So okay, I think my computer has just done something wrong. Okay, so now I've made a mess. Now let me clean up. Okay, sorry about the delay there. So here, this partial fraction, the inverse Laplace transform of it, is just going to be equal to the inverse Laplace transform of the Laplace transform of sine cubed. And so we know what this should be equal to. This will, in the end, this should be equal to sine cubed. But we can calculate it a bit differently, right? This is just going to be the inverse Laplace transform. So 3 over 4 times the inverse Laplace transform of 1 over s squared plus 1 minus 3 over 4 times the inverse Laplace transform of 1 over s squared plus 9. Okay? So what is this equal to? Now we can read off what these inverse Laplace transforms are, because they're standard ones. And they're just going to be equal to, so we'll have 3 over 4 here. Here we're just going to have sine of t. And then we have negative 3 over 4. And, all right, it's a bit of a trick involved here. We have to realize that the inverse Laplace transform of this function here is just going to be 1 over 3 times sine of 3t. Okay, so just to be clear, the inverse Laplace transform of this function is just this one here. And what was the point of doing that? Well, the point of doing that is that this is the inverse. So this inverse Laplace transform is the inverse Laplace transform of this function here, function here. And of course, what is the inverse Laplace transform of a Laplace transform other than that function? So this here is just directly equal to sine cubed of t. And by the way, this fraction simplifies to just 1/4. Okay, and that shows you how we can get this formula here using nothing other than Laplace transforms without integration. So a very powerful technique, and if you have any questions about how to use other functions, how to use this technique on other functions, just let me know. All right, thank you, and I'll see you next time.